Welcome everybody. It's a great pleasure for me to welcome Professor Uttam Manna, who is going to be our speaker today. Uttam Manna has been educated as a chemist, solid state and structural chemistry, and he received his master in 2009 at the Institute of Sciences in Bangalore. So I have had a chance to visit Bangalore 1.5 years ago. Nice place. So then he continued in the same field, I think also with the same advisor, to receive his PhD in 2011, again Institute of Science in Bangalore. After that he went as a postdoc to the United States. So he stayed at the Chemical and Biological Engineering Department at the University of Wisconsin-Madison with Professor David Lin from 2011 to 2015. So that was 2 different stages. And then in 2015, he accepted a position as an assistant professor at the Indian Institute of Technology at Guwahati, Assam. So this place is not only known for excellent tea, but also for excellent science. And I can say that because I had a chance also to visit there, attending a small conference and talking to many colleagues of his, a very nice place. So then in 2019, he was promoted to be associate professor at the same place. Despite his young age, Professor Manna has received a rather extensive list of awards and memberships and so on. If I read the whole list, we will have no time anymore for his presentation. So let me just mention that, of course, this is the reason why he is here this time and why he gives this talk, which will also be recorded. He was awarded an International Excellent Fellow of KIT. And so among his long lists, I would only like to mention that before that he was a humble von Humboldt Research Fellow with Michael Hirz at the INT. And he is also a member of the advisory board of Materials Horizons. So with this, I'm going to skip the entries of my rather long list and would like to ask Uttam to come in the front and provide his presentation. And in order that his voice is recorded as well, I hand over the microphone to him.
Thank you so much, Professor Christoph. It's a great pleasure to be here again and share some of our lab work, what we are doing in last few years. So before going there, I'd like to take this opportunity to thank Selection Committee for International Excellent Fellowship, which I received this year. And thank you again to you and IFG for hosting me and giving this opportunity. So today, I'm going to talk about how we can use the simple chemistry and play in the interface to derive some sort of functional properties, more precisely wettabilities, whether it will be liquid or the bubble. So I think I'll be able to convince you that chemistry will be very interesting here to play with all those kind of stuff. And before going there, this is the one of the glimpse of the natural beauty of our campus. So I think those who have already visited, like Christoph, you are there, so you have seen our campus, right? So this is just beside the bank of Brahmaputra. It's just a few kilometer away or barely. And if you see geographically, it is a far northeast part. And it's not only just famous for the tea, it's also a place full with natural beauty as well as natural resources, which is a very big contributor for our country's economies. Okay? So with that, I'll move forward. This particular topic, if you see, is started evolving formally probably 200 years ago. But some of this realization of this liquid wettability probably millions years ago, right? Because some of these features, some of this wettability is known from long time. Suppose this extreme water repellency, what is there with the lotus leaf or mosquito eyes or water strider or rose petal that are there for many centuries ago, right? It's just the thing is like our understanding towards these kind of interfaces is recent, and it's just the realization that this kind of interfacial property could be very useful for mankind to address some of these issues which we are facing regularly, whether it is the energy, whether it is environment, whether it is the health. Okay, I'll be able to convince you at the end of this talk. So let's start with the property which is commonly recognized, the extreme water repellence, what I have just shown you in the last slide here, that all of these examples are ability to extremely repel the water. But if you see their structure under electron microscope, you will see the coexistence of this micro and nano domain. Formally, it is called hierarchy in topography. Once you have that, and if you have a low surface top, then it can extremely repel. So that is the criteria to get the super hydrophobicity. But that is just the criteria, right? What's going on, that to understand, people did a lot of study and figured out that when you talk about such kind of extreme liquid wettability, whether it is water or say other liquids like oil or low surface tension liquids, their important parameter is the third phase, which actually minimizing the contact between the beaded liquid and the solid surfaces. So this yellow color is basically indicating that external third phase. If it is super hydrophobic, that external third phase will be here. Now, when we talk about the extreme water repellency, often we forget about another interesting property, that is the adhesion of this liquid on the surface, and that has a lot to do. So this particular property can be further classified into two categories. One is non-adhesive super hydrophobicity or extreme liquid repellence with ability to flawless rolling at a very low tilting angle of the substrate, where the tilting angle will be less than 10 degree, whereas in other case the tilting angle will be way higher to roll this same beaded liquids droplet, whether it is the water or oil, depending on what kind of interfaces you are dealing with. And if you see, nature has these kind of examples. So lotus leaf is an example of non-adhesive superadhesivity, and rose petal is an example of adhesive superadhesivity. One thing I've completely forgot, the formal definition of superadhesivity. When we define superhydrophobicity in terms of contact angle, then the contact angle has to be minimum 150 degree. Is anything that is above 150 degree, then it's called superhydrophobicity. And now, whether it's a non-adhesive or adhesive, that can be classified depending on how it is rolling the droplets, right? Whether lower tilting angle or higher tilting angle. And you believe me or not, this kind of ability of tuning these adhesive and non-adhesive properties, mostly in the literature done by modulating the topography, and that is not an easy job. And when you are dealing for like large scale productions, and it is really difficult, though we have a really advanced nanotechnology where you can precisely monitor nano and micro domains, but when it's come for the large scale production, it's a problem, right? So we thought, not topography, probably take another avenue, that is the chemistry. And in this particular topic, in this particular field, if you see, mostly people focus on the topography, not really on the chemistry. Chemistry part kept very blunt. What I mean that mostly people look for long hydrocarbon tail or its analog, fluorinated analogs, right? Just to satisfy the low surface energy. But we can play with this chemistry precisely to modulate different kind of liquid wettabilities, whether it's a heterogeneous liquidity in a submerged condition or it's in air, whether it's a homogeneous wettability with the anti-fouling property like slippery properties or not. Everywhere you will see the chemistry has a tremendous role, and probably within a half an hour I'll be able to convince you. And recently we wrote an article in Chemical Society Review that how the chemistry could be a powerful tool compared to the topography to associate different kind of functional properties along with these liquid wettabilities. These are some of the selected publication from last few years. So our journey started with this two simple molecule which is commercially available. This is the pentacrylate, and this is a branch polyethylene, where the amine groups are on the periphery, which has a much more density. Now, you allow them to react with a certain reaction compositions through this 1,4 conjugate addition reaction. What will happen? It will basically give you this beta amino ester type of linkage without producing any kind of side product. So you don't have to really think about how to separate out some side product and all, which is often a problem when you are thinking about some sort of chemical synthesis, right? So I like this particular chemistry because it is very simple to pursue at ambient conditions, and it doesn't really give any kind of side product. Now, at a specific reaction composition of these two reactants, you will see the sol-gel conversion through this nanocomplex formation. As you can see, it started with this clear solution and it's forming a gel, and you can give a different kind of shape. As you can see here, we can give a shape of a bunny, and this bunny is initially hydrophilic. That's the reason you can see red color water is soaked. But after the post-modification, because it has a residual acrylate group, it can extremely repel the interface. So not only that, if you eroded the top surface, the underneath surface is also capable of repelling the water droplet extremely. But our aim was not to prepare this kind of monolith and play with this bunny's wettability and all. More, we are interested on this reactive nanocomplex. And you can see the growth of the reactive nanocomplex, and you can precisely modulate that just by changing the reaction conditions, even the reaction solvents and some sort of additives. We can make it the faster or slower, and that's the way we can achieve some of this surface sol-gel chemistry and getting the porous coating. I'll come to the next slide and explain that part. Now, this nanocomplex is not like other regular nanoparticles and nanocomplex. This nanocomplex has a residual acrylate groups. And as evident from this FTR spectra, if you see this CH stretching for the beta carbon of the vinyl group, that is basically appears in 1410, which is unambiguous signature. And you can see another signature for this carbonyl, but once it's go for this 1,4 conjugate addition reaction, carbonyl remain as it is. It's just the vinyl group is vanished, right? So this carbonyl act as a internal reference, and if you basically normalize this spectra with this particular IR positions, then the depletion of this signature at 1410 is precisely tell that this residual acrylate groups is reactive in nature, and you can react with a small molecule to modulate the surface chemistry around this nanocomplex also. Now, our aim was to deposit this nanocomplex at a different time frame, premature those reactive nanocomplex, so that let them do some sort of cross-linking gelation at the surface and form some sort of porous polymeric coating. And that's what exactly we got. Depending on the solvent system and additives, we can accelerate this sol-gel process, and we got this reactive porous coating. Now you go for the different kind of chemical modification, again using this 1,4 conjugate addition reaction with a different kind of alkylamine, and you can associate this kind of non-adhesive superadhesivity as well as adhesive superhydrophobic. As you can see here, these are like all these contact angles are above 150, but if you see this roll-off angle, that is now changing significantly depending on this hydrocarbon tail length. It's just whether the carbon length is 18 or 10 or 15, that decides that what would be your superhydrophobic nature. Will it be adhesive or non-adhesive? And it was really difficult to achieve in earlier. People only used to do it with the topography. But here, with this simple chemistry, you can precisely optimize this adhesion property as well as this contact angle extreme repellency of the water. Now, how it is happening is basically how you attain this Cassie-Boxter model, which is the kind of responsible for non-adhesive superadhesivity, and this Cassie-Wunschel transitional state. Basically, how you are modulating or managing this external trapped air in this porous coating, and that is precisely maintained through this chemical modification. As you can see, the fraction of contact area of the beaded liquid on the solid surface that is varying regularly depending on this change in this hydrocarbon tail length. But only problem with this particular design is that we cannot really modulate this wettability and then this adhesion property orthogonally. It's a single chemical modification giving two different properties, right? So that way, we thought like let's go for another kind of way of modulating that. What we can do, we have taken this particular same porous coating. Firstly, earlier we have only explored this acrylate group. Now we are exploiting the residual acrylate and residual amine both. So first, when you go for the modification with octadecyl amine, you get non-adhesive superadhesivity, extremely repelling above 150, and also the rolling angle is less than 10, it's around like 4 or 5. And then you take this another modifier, the small molecule, it has an acrylate group, it has this hydroxyl group. So hydroxyl acrylate, which can readily react with this amine group, and then it can make this interface adhesive, maintaining this extreme water repellency. So water repellency remain above 150, you can see the roll-off angle drastically change, almost twice, and you can see the fraction of contact area with the solid and liquid, that is also significantly changed. Not only that, you can precisely measure the force of adhesion between the beaded droplet and solid surface, that is almost twofold change. Now, not only just the playing with this water repellency and adhesion, you can also associate the fluorescence property if you choose reasonably this modifier. Suppose here just the glutarylate, which gives this imine bond, and the N2 pi transitions also give some sort of fluorescence property, and that's the way it allows you to design some multi-level anti-counterfeiting interfaces. How? Let's start with this particular example. So when I say like adhesive and non-adhesive, it has not only the adhesion properties, it also gives another interesting property, this optical appearance when you are submerging underwater. It will not going to, like, water is not going to wet the interface, but when you submerge under water, the light which is incident on this interface, it's realizing these internal reflections, and because of that you see the shiny appearance. It will be more when you have a more trapped air, right? For non-adhesive interfaces you have more trapped air, more internal reflections, and it will appear more shiny, whereas for adhesive one it's less shiny. Now, probably it is not very clear here, but you can see in the scheme, we can spatially, selectively, we can modify whether it's a monofunctionalization or a difunctionalization. Depending on that, you can play with these adhesions. And just take a look in this particular video, you will see that initially, you cannot really recognize what kind of information is provided. But once you submerge under water, not only the shiny and only the portion where the dual modification that appears, the smiley face. Look at here, you put the water droplet that acts as a lens also to visualize a tiny pattern which you left behind in the surface, and when the water droplet removed away, your information is vanished. So that can be a smart way of hiding information on the interface, and that can be useful for anti-counterfeiting applications. And what we did, we have associated these pattern interfaces with fluorescence property to develop this multi-level anti-counterfeiting interfaces. Now, just to summarize this particular work and precisely tell that what is the difference between a conventional hydrophilic, hydrophobic, or hydrophilic superhydrophobic pattern versus this adhesive, non-adhesive superhydrophobic pattern, is that these particular interfaces, which is known, which is good for many applications, but they can easily get foul when you expose to the dirt and dust and the water, because water integrates precisely on the hydrophilic domain. Whereas in these particular interfaces, extremely water repellent, whether it's adhesive or non-adhesive. So it never get wet, and it's self-cleaning all the time. So for outdoor applications, for these kind of anti-counterfeiting applications, these kind of interfaces will be much more desirable. And these are like rare design which can be only achievable through this simple chemical modification. Now, I'll shift my gear here to go and introduce another topic, which is underwater adaptive superoleophobicity. And this is the work is introduced or motivated from Professor Li Jiyoung, who introduced this particular property in 2009. What they found that the phi scale has inherent ability to extremely repel oil droplet underwater. And once this particular discovery was introduced in literature, people realized hydrogel is the best candidate because that can adhere a lot of water and it can minimize the contact between the solid and the oil droplet. And that's the way, if you see, right after this invention, many hydrogel-based design came into the picture. Also some sort of multi-layer coatings which are derived from polyelectrolytes. But they are not good in terms of the durability. They often suffer from the durability. So we thought, like, why not this covalently cross-link polymeric coating which is remain chemically reactive, and explore this porous coating in designing some adaptive super oleophobic interface. And the kind of instrument of this work is sitting here in the audience, and she basically took this challenge and to derive and develop some of these adaptive coating. Adaptive coating means here this super oleophobicity, precisely you can play with these adhesions. And when you play with this adhesion, that give you a platform to visualize amplific molecules to the naked eye. You can really tell in your water, if you take some aqueous contaminated water which is contaminated with a different kind of surfactant, you can precisely tell which one has a cationic group, cationic surfactant, anionic surfactant, or facile amplifiers. You don't need any kind of sophisticated instruments. Okay, let's see what is the designing she has introduced. So what she did, she took this dual reactive coating and modified with these particular small molecules which give this tertiary amine which undergoes easy protonations and give the cationic charge under acidic conditions. So now if you introduce some sort of anionic surfactant, say SDS, the anionic head will interact with this cationic charge which will be induced after acidic exposures, right? So this cooperative effect through the ionic interaction, and then hydrocarbon tail will be exposed. Here the hydrocarbon tail is the anchoring point with the oil, because this kind of oleophilic kind of interactions, right? And that's the way this non-adhesive super oleophobic coating will transform into adhesive super oleophobic at underwater conditions. She also found another control study where she introduced these two carboxylic acid group here. At alkaline conditions, it could be dissociated and give the negative charge. Now you introduce this cationic surfactant. What will happen? The cationic head will interact with the surface of dissociated this charge of this carboxylic group, and it will also provide this hydrocarbon tail to interact with the beaded oil droplet, and that's the way you will see this change in the adhesions. So next, she developed this pattern interface where half of the coating was introduced with this modification 1, which has this cationic kind of functional groups, where another case is modification 2, where you have these carboxylic acid groups, and in alkaline condition it can dissociate, right, and give the negative charge. Now see these particular demonstrations where this pattern interface was placed in a submerged conditions in an aqueous phase, has a 250 micromolar SDS, negatively charged surfactant, and at pH 5 put the oil droplet. When you put the oil droplet in this modified interface 1 where I have the cationic, there you see the droplet is stuck, it's not rolling. Okay? Obviously the surface is tilted at 10-degree angle, whereas for modification 2 you will see you put the same size of the liquid droplet and instantly rolling. Now if you have the D-tab here, where if you suppose the cationic charge, and if you have the pH is somewhere like alkaline 10, then you will see the opposite phenomenon. And if you see that both the things are getting adhesive, that means both the surfactant is there, right? So that's the way you can basically differentiate the cationic head and anionic head of the ionic surfactants. Then we thought, like, okay, that is good. What about other type of surfactant like Facile amplifiers, the bile acids, which is a biomarker for interstitial disease, right? So in that case, we introduce some sort of other type of design. If you see here, we have a design where we start with the adhesive underwater super oleophobic. So here we start with one modification, which is the glucamine, which is a neutral hydrophilic molecules, and you have this alkyl amine of a different tail length. Depending on this tail length, whether the N3, the butyl or pentyl, or this is octadecile or decile, it doesn't really matter. So depending on that, you can play with this force of adhesions, right, of these interfaces. And what is known that this cholic acid, which is a facile amphiphiles, one side is hydrophilic, another side is hydrophobic. This hydrophobic fragment can undergo this cooperative assembly with these long tail hydrocarbons. And that way it can, you can see only this hydrophilic part is exposed, and once that is happening, then the transition of your adhesive interface into non-adhesive interface, because you are precisely playing with the surface free energy of this coating, right. And that's the way you can, if you see here these particular demonstrations, initially it was adhesive, you put the oil droplet, nothing is happening, then you put the cholic acid. So see, add the cholic acid here, and once the cholic acid is placed, then the next place of the same coating, put the another droplet, just to make it a little faster. Yeah. You will see that once he is placing this oil droplet, then it immediately is rolling off. So the same surface, how you are precisely performing this chemistry on the top of this surface, that allow you to sense this cholic acid, one of the bile acid, and you can sense in the range, in this entire range, and this window can be modulated just by selection of these modifiers, whether it's a butyl or this is octadecile, right. And the limit of detection is 4 micromolar, which is way lower than is a normal range in our body. And if you see whatever the regular interfering agents are there, it doesn't really interfere in this kind of sensing process, because here this kind of interactions is very selective, which doesn't really perturb by neither this acidic, alkaline or urea, glucose and all those kind of stuff present generally. Now these are all I've talked about, extreme repellency of water or oil, right. Now I'm going to talk about air bubble, okay, and how you can play with the repellency of the air bubble under water and play with the adhesion, and that could be useful for water splitting, electrochemical water splitting. And that has been done in collaboration with Mizuki from Japan NIMS. We all know about this electrochemical hydrogen evolution. These mechanisms are known from long time, and this is something we are not going to play with. What we are going to play with is just how quickly we can release the product from the electrode surface. That is our ball game. So in this water splitting, the product is hydrogen, and which is a gas. It has a natural affinity toward the solid surface, okay. And when that is there, it can block the electrode surface, this catalytic interface, and make it inert, because there is no contact between the electrolyte and then this catalytic surface, unless and until this bubble is displaced from this electrode surface. And those who have performed this electrochemical HER, they have often seen its hydrogen bubbles produce, become bigger and bigger, and then it displays. I think many of us also have seen, like when you were drinking some carbonated fluids, if you shake it, you see the bubbles are forming, and it's either on the container, right, and it's forming a bigger droplet and it's coming into the top, right. It because the bouncy force that drag it out from the surface, right. So this is the same mechanism here. The bubbles are forming and it's becoming bigger and bigger. That means the bouncy force is becoming predominating and it basically compensating this adhesion force, and that's the reason it's detached. But during that process, millions of bubbles are coming out, and it will feel some sort of shear trace. And if you are physically depositing some sort of state-of-art catalyst, they are naturally going to detach, right? So the performance of electrode will be a problem. So what is the remedy? Either you go for this tailoring sonication so that you can go for the early detachment of the bubbles, or some sort of this kind of conical shape of this topography, which is not always possible with all different kind of catalytic surfaces. Other solution is like play with this bubble repellent coating, which is introduced recently based on this hydrogel formation on the electrode surface. As you can see here, they took this polyethylene imine and glutaraldehyde, it undergoes this imine formation, but that chemistry is still labile, right? If you put it in a acidic conditions or even in a water for a long time, we know like imine bond will not be stable for a long time. But for the proof of concept, you can see like once they're depositing on this nickel foam, it's really play with modulate this bubble repellency, and their LSV showing that significant improvement in terms of H here, right? And when you do these resistance corrections, then the performance is similar. So it's not a catalytic performance, it's just the bubble dynamics, how you play. And since then, different type of materials have been deposited, whether virus or other polymers or even these bacterial fibrils and all. But none of these have a ability to directly modulate something important property, that is a bubble adhesions. It can only play with the bubble wettability. So then we thought, let's go with this particular design where we can go for growing the multi-layer construction of these nanocomplexes on this nickel foam and play with this chemistry to associate different kind of functional groups so that we can play with both bubble repellents and bubble adhesions. And we remain quite successful here. You can see like this is the kind of optimization conditions. I'm not going in details, it's already published. So what I can tell you in short that this bilayer number and then the dilution or the say like the concentration of this nanocomplex, that really play a role to get a optimum deposition without blocking the pore of the nickel foam, inherent foam. And you see this association of this nanocomplex which leave behind some of the pores, which is important, right? And after deposition of this reactive coating, you will see the bubble repellency little bit of improve in terms of this uncoated coating. But when you go for these single modifications with these modifiers or this type of modifiers, which is called as a dual modification, the DMC is abbreviated to dual modified coating, and these are like single modified coating. We found this is the kind of modification where you have this tertiary amine in both sides, then you see this bubble repellency is maximum 162, and what we also observe that irrespective of this single and dual modification, they all give super hydrophilicity. But that doesn't mean that all these interfaces will give super aerophobicity. So earlier if you see, people used to apply this equation where the aerophobicity plus water contact angle, that will be summation of 180. So if you are making some interfaces where contact angle, water contact angle is 0, people thought it will give you super aerophobicity. But through this particular study, we found like not necessarily that is correct. And you can come up with a different type of super hydrophilic interface, but they are distinct in terms of surface free energy. The surface free energy is a very important term here because that decides how good your interface will be hydrated. More and more it will be hydrated, it will minimize the contact between the bubble and the interfaces, right? And our assumptions was quite correct. And when we put this static bubble and measure the force of bubble contact, bubble adhesions force with these differently modified interfaces, we can see this gradually the force of bubble adhesion is decreasing, and then you see this the surface free energy is gradually increasing. So you have a higher surface free energy, you have a least force of adhesions. So these, based on this particular study, we thought like we are in a right spot, then study these nucleated hydrogen bubbles, their growth, and then how they can easily detach from these surfaces. Whether you can pre-detach or you can detach this the hydrogen bubbles much earlier than this bouncy pore dominated, right? So as we have studied, experimentally validated with this static bubble contact angle, we wanted to see what happened for the nucleated bubbles, right? For that we did this simulation using these Young-Dupré equations, and simulation data is also showing the similar kind of trend, and the EPOS number that tells that this particular phenomenon is not depends on this bouncy force, rather is a capillary force, okay? So because of this, you can see the coated foam, the bubbles can release way early related to this bare nickel foam. For the bare nickel foam, the bubble size is much bigger, around 3.5 millimeter, whereas this one is a micron range, right? Because of that, you can see this LSV is improved. The current density is a given potential is very high, improved significantly. Not only that, the over potential is also improved with respect to the bare and then reactive multi-layer coating. Now you can see that for the bare, these are the big bubbles, and here you can barely see the bubbles. So let's take a look in this video. So this is basically for the bare nickel foam, where the bubble size are quite bigger. These are like hydrogen bubbles. Now you see the second half of the movie. Under same experimental conditions, the bubbles are way smaller, and the production of the hydrogen is much more compared to the bare bubble. Now, one of the referee asked, like, how do you show that this is like, the coating doesn't have any catalytic contributions? So for that, we did this simple study here. See this reactive coating, that doesn't really show any kind of, this kind of performance, right? And then now just the simple hydrophilic modifications, which doesn't known for the catalytic ability, that give rise to this improved performance. To further verify what we did, we took another modifier, that ODA, octadecylamine. When you go for the ODA modification, then interface suddenly become this, bubble philic, the affinity for the bubble will be much higher, right? The contact angle of the bubble will be much lower, right? In that case, you see the performance is even poor than the bare. So the same coating, it's just the modifier you change, you play with the bubble repellency or bubble affinity. Depending on that, you see the improved performance or the poor performance, right? So this is not the catalytic performance of the coating, rather how you play with the bubble dynamics. And you can see like here the resistance, right? Whatever you have improved because of this coating, that if you incorporate it in this LSV, then you see the similar kind of performance. So that again tell that this is not just based on the catalytic performance, it's just the resistance which is created because of the bubble adhesion. And once you play with that, then you can minimize this over potential, and this coating remain quite stable. And even after this stability test, we perform this LSV, they remain very nearly similar. It doesn't also depends on the nature of the electrodes. You can also use the carbon cloth or carbon paper, you see the similar tendency. Not only that, if you see this comparison table where in the literature mostly people go with the catalyst embedded coating, and this is the catalyst free coating. And if you see this approach of control manipulation of adhesion and the wettability, bubble wettability really help us to improve its performance with respect to over potential as well as the stability. So with that, I'll go to the next story, the last story. So far, whatever I said, it's extreme repellency of the liquid or the bubbles. Now I'm going to talk about the interface where it is a homogeneous wettability, but still remain anti-fouling. What I mean, not necessarily like water or oil has to be repel extremely above 150. It can be way lower than that, but once you tilt this interface, instead of rolling, you see the sliding of the droplets, okay, and leave behind no trace of those liquid, beaded liquid. Now, what we want to do, addition to deriving that kind of interfaces, whether you can introduce some pattern which will be selective to specific liquids or certain type of liquids, whether that is possible or not. So this particular work was inspired from the early discovery from Zona Eisenberg in 2011, if I correctly remember. So what she did, she inspired from this Nepenthes pitcher peristrom that has an interesting property. So I think many of you know that this pitcher plant is carnivorous. It can eat the insects. Now they don't have the hand to catch and eat, right? So what they have this kind of this pitcher which is full with sticky digestive juice, but you have to get the prey inside, right? So for that, this peristrom is decorated with a slippery property. Once the insect land there, they slip into this pocket, right? So in that particular design, what you have this kind of topography, and there the lubricant is filled, and that make this interface extremely slippery. Okay, so inspired from that, what Zona Eisenberg and her team did, took this kind of porous and functionalized coating and lubricated with this Krytox, which is fluorinated, and this substrate also derived from the fluorinated molecules. And then once you put some sort of probe liquid with the water or oil, it started sliding. So since then, people wanted to explore this particular field, and in general, you come up with this porous and textured surface, go for the complete hydrophobization, it's a highly hydrophobic or super hydrophobic. Then you go for the lubrication with the silicone oil, Krytox, or any type of the oils what you can think of, and then you infuse it, and then depending on the compatibility of the surface as well as the probe liquids, you see this sliding behavior. The problem is this lubricant is a liquid in nature, so when you put the probe liquid, it will be contaminated, and over the time it will leach out, so it will have a shelf life issue. Okay. So what people thought, whether they can develop some sort of solid slippery or quasi solid slippery coatings. That is there, few approaches are there, but the problem is in those cases the self-healing ability is not there, and the top of the interfaces modeled in the chemistry is extremely challenging to us. So what we thought, come up with this particular polymer which is crystalline in nature because of the hexagonal packing of this hydrocarbon tail, depending on what is the length of the hydrocarbon. If it is anything like 15 or say like 18 or say 22, in that case it can nicely go and hexagonal packing. You give the crystalline domain, and it also undergo phase transition. At the elevated temperature around like 50 degree, it can, the crystalline domain and basically disturb, it undergo molten state, and when it come to again lower than that phase transition temperature, it solidify. So this is one of the component which is helpful to go for the phase transitions and crystalline network, and which will contribute to this attending slippery property against wide range of liquids. Another interesting component is this maleic anhydride, which is helpful to modify this polymer with a different type of small molecules and play with the surface free energy, and which has a lot to do in terms of these anti-fouling interfaces or the liquid repellence or sliding abilities. So with that, let's go ahead with this design. So you can see we have a substrate, we can develop this porous network, which is our bread and butter we are regularly doing in our lab, and then infusing this cum polymer inside this porous polymeric coating. And once you have that, depending on this category of this long tail hydrocarbon, you can have a sliding property towards the polar or non-polar. If you have anything less than that, you don't have any sliding property, and if you have a something like the hydrocarbon tail length is around 22, then it will repel, it will slide even the oils. So sliding oil is always a difficult job, but that can also be achieved. Now that's the way you can come up with this omniphobic solid slippery coating. As you can see here, this is two example where you took the water, which is surface tension more than 35. It is way more than 35, it is around 72 millinewton per meter, and you have a ethanol, which is way lower than 30, right? And if you put them, you can see the contact angles. They are not really that extremely repellent, right? But when you tilt them, you can see they can nicely slide off, okay? Leave behind no trace of neither water, neither ethanol, okay? Now, what is the reason behind this property? That has not been studied thoroughly in the literature so far. Is it the roughness or say like the smoothness? So we studied this material and we found that roughness is around 22 nanometer, which is considered to be low rough interface, and we have an ability to modulate the roughness in this current design. So this maleic anhydride and these long tail hydrocarbons that acrylate, alkyl acrylate, that composition we can vary, and depending on that we can play with this crystalline domain and this roughness. So in one composition you can have a roughness around 0.4 nanometer. So it is way smoother interfaces. In that case, the sliding angle against the water still remain, but if you see against the ethanol, it is not working, but you make this interface much smoother. So it is not roughness, it is something else. What is that? So we found that when we gradually vary the molar composition of this maleic anhydride, crystallinity is there because this part is still there quite weight to make the crystalline domain, but probably the crystalline domain size is varying, and that contribute to changing this roughness. As you can see, roughness is gradually decreasing. Okay, this is the roughness domain, and you can see gradually decreasing with increasing the molar fractions of this maleic anhydride. Okay, so our expectation is that when you are decreasing this roughness, the slippery property will be better, but in reality it is not happening. Why? Because if you see, there are another axis that is for surface free energy, that is increasing. Okay, when you go for maleic anhydride more, this is more polar group, right? The surface free energy will be increased, and because of that you will see this interface becomes slippery to only water, not for the low surface tension liquids. So with that particular understanding, we thought, okay, our interface is chemically reactive in nature. Now let's go for the post modification and see its behavior. So initially you started with an interface which is omniphobic in nature. Okay, it slides ethanol, water, and all different kind of liquids. But when you modify the glucamine, then it compromises the sliding behavior against only the low surface tension liquid, where the liquid surface tension is less than 30. Okay, and you can see this is the unmodified, and then after glucamine modified it compromised. But once you heat it up, this interface again, then it regains its property. So what is going on here? So if you see, when we have started with this particular coating before the modification, it's remained hydrophobic. The roughness is remain somewhere around like 22, 23. Then you go for the hydrophilic modification, you are not anyway playing with anything on the roughness factors, right? So the topography remain very similar, roughness remain very similar. What's happening, the interface become hydrophilic in nature. The water contact angle is dropped down from 110 or around that to something below 90. And the surface free energy that is elevated now is above 30 now, okay, around from 22 to 30 now. And then when you are cooling down, heating and cooling, at that point you can see it again become hydrophobic, and the roughness remain very similar, it's just the surface free energy again dropped, right. So that means on the surface the functional groups are getting altered, and that is also verified with this ATR FTR study. So before the glucamine modification, you can see this is a predominant signature for these maleic anhydride groups, right, the symmetric stretching and asymmetric stretching. Now after the glucamine modification, which is expected that maleic anhydride will go for the ring opening reactions, right. So it is compromised quite a bit, you can see here, and when you basically heat treated and cooling down, then again it is stronger. It's not stronger as like the before, which is not possible, but it's stronger. So that means reorganization of this functional group on the top interface is happening, right? And that has been, so this particular study done with respect to this invariable signature, that is the carbonyl group coming from ODAC, octadecyl acrylate group, right? So that clearly says that this change in IR signature indicating the reorganization of the functional group. So our postulate is like this. So we have a crystalline network that have a limited amount of this maleic anhydride group that is reacting with this glucamine, and it cannot really go deeper inside, right. So whatever is available in the surface, that is getting modified, and when you are heating up in the molten state, it undergoes some sort of organization, reorganization or a diffusion, right, and that helps to reorganize the chemical function in the top, because in naturally any surface you keep it, they always want to keep the top surface, the surface free energy low. So if they have a availability of some sort of functional group which is not like glucamine, they will be exposed out, and that's the way we see further dominance of this maleic anhydride group. So taking advantage of that, what we did, we make a pattern, spatially selective pattern. Now this pattern is only visible to ethanol, but not to water. So it's a same pattern, same interface, one liquid can see the pattern, other liquid cannot really see. you know. So that is very difficult to achieve, but you can see, like, you know, we are putting the water droplet and you don't see any trace of the water droplet here. But when you put the ethanol, then it can find those spots and it can take a shape of the A, that arrangement, right? And taking advantage of that, you can, so this you know, you can recreate that or rearrange this functional group on the top surface repeatedly, right? So doing that, you can erase and rewrite this pattern, you know, a number of times. So as you can see, like A pattern, and then erase it, and then you make it another pattern, T shape, and that's the way you can do it many cycles, right? Now, what is the use of that kind of interfaces, right? So what we thought that one of the depiction, there are many things can be done with this. So this is the kind of new avenue which has been opened up. So just to show its potential, you can think about sorting of two different liquids, okay, with these interfaces. So you make a pattern, okay, you give a different path. For the low surface tension liquids, it can really wait and follow this path. When you put the high surface tension liquid, in that case it can follow other path. So that's the way two distinct liquid can be sorted out. And you can see, like, you know, here these liquids can follow this path, and this group of liquids can follow this particular path, right? Not only that, you can have an array of these spots, and you put this oil and water droplet together. You will see the breaking of cleaving of this oil droplet from water, and you can collect the oil free water. So it could be something like oil catcher, right? And you can also, you can see, depending on the concentration of the oil, you can see the length of this oil strip is varied. So qualitatively also you can tell that, you know, whether you have in the contaminated water it is a more oil or less oil. And many other things is possible. Just to give you another glimpse that what we are doing further in our laboratory, we're also playing with this underwater super oleophobic coating, which is not only playing with the adhesion and the extreme repellence, it also play with the mechanical property. You can make the material extremely hard when you are depositing on a highly deformable substrates. You know, that is what, again, Angana was one of the lead contributor in this work. And this is another work where we can release the small molecule, the drug, in two different mechanisms. One could be continuous, another could be pulsate. And this is known from long time. The pulsate release or trigger release and the continuous release is not new. But the strategy what we adopted here, that you can do the pulsate release when your stimuli is on. When your stimuli is off, your pulsate release is off. Again, you switch on the trigger, your pulsate release will be on. So that is something is new, because when you go for the burst release, you exposed to some sort of stimuli and the gate is open and it is continue to release everything, right? But this is fundamentally different design, and that has been done with this liquid crystal association with this porous coating, and where and how you are loading these drug molecules. Another one where we have introduced these highly hydrated coatings to separate liquids irrespective of difference in surface tension. People often talk about the separation of oil and water, but they are quite different in terms of their surface tension. One probably 72, another is 22 or 30. What about a liquid mixture where the surface tension difference is only about 2.5? Can you differentiate it? For that, you need a very tolerant underwater super oleophobicity. That is only possible when you have a very highly hydrated environment. That is can be also be achieved, and this is recently accepted in advanced functional material. Then also we have introduced this kind of water repellent coating in the COF. There's another porous crystalline material to associate the selectivity towards the oil phase and repellency towards the water phase, and that's the way you can separate the emulsion efficiently. So these are some of the piece of work which is going on, and we also have some active collaboration with industrial partners for commercializing some of this invention what is going on in our institute, in our lab, and some of our work has been showcased as a cover page in different journal. With that, this is the most important part where these are the people who are instrumental behind this work. I'm just presenting the work on behalf of my students here, and you can find us in this particular website. And I'd like to thank my department. I'm also affiliated with other associated with other departments like Center for Nanotechnology and the Health Science and Technology. And I would like to thank again to Professor Christoph Fuhl for hosting me here, and the selection committee for this international affair in KIT, and as a whole the Cultural Institute of Technology and all my funding agencies. With that, I'd like to thank again, and if they have any query, I'd love to address them.